Swayam Prabha. Digital India. Educated India.
Now let us go and start with some other important topic in the designing of the instruction set. Like how do you decide the number of registers, right? For example, Intel, the architecture you are seeing has 8 general purpose registers, but there are RISC architectures which have 128 general purpose registers, right? The number of so this is side. How do I decide? This is the question that we would like to answer. How do I decide the number of GPRs? GPRs essentially stands for general purpose registers. You had seen an architecture in the previous semester where you used only 2 registers, correct? It also worked, right? So let us now debate, like I just want to have a discussion now on what are the factors that will influence the number of general purpose registers. What are the facts?
So basic operations that we could do, because we couldn't do division back in, now we are able to do division because we have EDX, EX and.
So the first question here is that we are already seen what is a load store architecture versus a normal non-load store architecture. What is a load store architecture? Only 2 instructions can touch memory, one is load, another is store. All the other instructions work with registers. If that is the case, then we will need lot of GPRs. So in a load store architecture, we will need lot of GPRs. Many of the RISC instruction architectures are load store architectures, right? Why should RISC instructions be load store? Why should the RISC ISA be load store architectures? Because they are of fixed length. Almost all the instructions should be of fixed length. So I cannot afford to have memory operands along with registers. If they are constant length, I should know where the destination is, where the source operands are, my decoding should be easy. So if I have a load store architecture, all these things become easy. So many of the or almost all or all the RISC architectures are indeed load store architectures. The moment I have load store architectures, then I need to have a lot of general purpose registers, because only 2 operations can use memory as an operand. The remaining things have to use register as operands, right? So that is one first part. So there is a need for RISC architecture because my execution will become faster, my decoding will become faster. The moment I have RISC architecture, then it's of fixed length. So I would not like to have too many types of operands there, and so to make my decoding easy, I go through to the load store architecture, and the moment I have load store architecture, I need lot of GPRs. So this is one story, right? Now what will happen if I have lot of GPRs? Okay, so let me just take the next point here. So a GPR, all the GPRs are stored in something called a register file. Okay, an advanced course in computer architecture will teach you how to design register files. Okay, right? So there are many registers in this register file. So when will this register file be accessed? Whenever I want to fetch data or when I want to store data. So there are 5 stages in the execution of instruction. Fetch the instruction, in which register file will not be accessed. Decode the instruction, fetch data, at that point the register file will be accessed. Execute the instruction, again register file will not be accessed. While I want to store back the data, again register file will be accessed. So at 2 points the register file will be accessed. And when I want to access the register file, I should basically say which register I want to read or write from. In the case of data fetch, I am going to read. In the case of writing result, I am going to write. So, I should tell which register I need to read or write from. Okay. So, what I do, I give a address for that register. So, let there be 8 registers, say R0, R1, R2, R3, R4, R5, R6, R7, I have 3 bit address for this register. These 3 bits are basically decoded to find out which register I should enable, right. So, register there is always an enable bit, then only you can go and read or write from it. So, which register to enable will be done through this decode bit, correct, right. So, there is a decoder, right. Now, if I keep increasing this, so this is now what 3 to 2 power 3 decoder, right. If I have a 128 GPR, it actually becomes 7 to 2 power 7 decoders, right. As I keep increasing my number of GPRs, the decoding will become more and more complex, right. So, what I mean to go and access that register file, again access means read or write, okay. Access is a common word used for read or writing into any resource. What do I mean by accessing the register file? I need to give the address of the register and then I have to go and access it. After giving the address, there is a decoding happening which basically tells which is the register that you want to go and access to. It goes and enables that register, and the decoding happens from a k to 2 power k decoder. So, the total time to access the register includes this decoding time. Are you able to follow, right? So, if I keep increasing the number of GPRs, what will happen? This decoding time will increase slightly, but it will be logarithmic, but it will increase. But very importantly, the area of the decoder will exponentially increase, right, because I need 2 power k lines, right. So, there is an exponential increase in the total area that is required to implement the decoder. So, as I keep increasing my registers, number of registers, what could happen? I will land up with a circuit with consuming more power, more area and also less performance, right, because the depth of the circuit also increases, right. So, this is the other side or implementation side problem with number of GPRs, right. So, there are plus and minus of how many GPRs should I include, okay, right. So, if I include lot of GPRs, let it be there, then lot of power area is getting wasted and your performance also will take a hit. But in the same time, if I have very less number of GPRs, what will happen? Suppose I am computing with say 10 variables, right. If the variable is in the register, then I consume say 1 unit of time. If it is in the cache, I approximately consume 5 units of time. If it is in the memory, I consume close to 50 units of time. If a variable is in the register, it is very quick for me to access. If it is in the cache, it is 5 times slower. If it is in the memory, main memory, it is 50 times slower, correct. So, what will happen is, if I have lot of operands which I need to operate upon, lot of variables, the compiler would prefer to have it in the registers. All the variables that need to be used in the near future, the compiler will try to have it in the registers, because quickly I can keep accessing it, and after I finally say, suppose I am having something like a equal to 1 and there are many f1 of a is computed, f2 of a is computed, f3 of a is computed, and then finally at this point. So, right from this point a equal to 1 till I finish computing f3 of a, the compiler would like to keep that variable a in some register. After that it will go and update into the memory. After end of this, you can go and say move that register into memory or store that register into memory. By doing this, what happens? Every time I want to access a for computing f1, f2 and f3, that a will be available in the register and I will get it very fast. If it is not there in the register, then what will happen? I have to go to memory which will become 5 times or even 50 times slower, depending on whether it is in the cache or not. You are getting this? Are you able to follow? Now, if I have lot of variables and very less number of registers, then what will happen is, at some point of time, I do not have enough registers, so I will be forced, the compiler will be forced to move the variable back to memory. For example, suppose I had only 3 registers, suppose I have only 3 registers, but I have say something like A equal to 1, B equal to 2, C equal to 3, D equal to 4. I want to compute f1 a b c d, f2 a b c d, some function f3 a b c d. I can store only a b c, so when I am computing even f1, I will first compute part of a, b and c and assume it is a load store architecture, right. I will first compute a, b, c keeping them in register, then I have to remove off some b out to memory and bring D from the memory and then finish the remaining part of the computation, right. And then similarly when I am doing F2 or F3, every time I need to do this, okay. I do not have enough registers to maintain my temporary my variables there, and so as a result of it, I go and write back some variables to the memory and fetch it back whenever it is necessary. This is called register spilling. Okay. Register spilling is the name for this phenomena, where I have limited GPRs, general purpose registers. I have more variables that I would love to store as in the general purpose registers because I am going to use it in the near future, but I do not have enough registers. So what happens is, at regular intervals I have to go and save some of these registers into memory, that means the corresponding variables I am storing back into memory and fetching the new variable from memory to do these computations. And this becomes very important if I have a load store architecture, because in normal operations like add, subtract, division, multiplication, I cannot use general purpose register, I cannot use memory operands. So every time I want to do any computation, then I have to put that operand into a register, and if I do not have enough registers, then we will end up with what is called as register spilling, and because of register spilling, what will happen? Your performance will degrade, because every time I have to go to memory and bring it from memory. Your compilation also will become extremely difficult, because when the compiler is generating, for example, the code for A, B and C and D, it does not know. So it has first fetched A, B, C. Should I fetch A, B, C or B, C, D or A, C, D or B, C, D, I do not know, right. Which combination should I keep, and when the new variable has to come, which should I evict? So all these type of things has to be done by the compiler when it is generating the code. Are you able to follow this? So that also, so the compilation also becomes extremely difficult when I have less number of GPRs, right. So register spilling really kills. Okay. So the objective is now is that, so as I keep on telling you, computer science is also communist science. If you get something, you lose something. There is always an act of balance, and that is why this course becomes interesting, right. Any course in computer science becomes interesting, right. So today I have lot of benefits by having GPRs. I have lot of problems while maintaining these GPRs, right. So how do we strike that balance? I cannot have too much, I cannot have too small. So what is it? Why should I have 128? Should I not have 64? Can I not have 256? So how do you come out with this decision? And that is very, very important. And the ultimate objective is that I should not overdo it, nor should I end up in a situation where I am having register spilling. Correct? Is it fine? So how will we solve this problem? Okay. So I am going to go, so somewhere I am trying to collect algorithms, graph theory and all here. Okay. So normal computer organization course does not teach these things, but I will teach you these things because these are very, very important and crucial, because how architecture is designed using some of your theoretical fundas. Okay, so let us go back. So let us now start. What is a graph? Okay, Palagat, tell me what is a graph? Collection of vertices. So graph G is a tuple V comma E, where V is a set of vertices and E is a set of edges connected to them. Okay. Now let me introduce a new type of graph called interval graphs. Okay. So let this be the number line, or this be the, okay, this is a number line. So I draw several intervals. Okay. Each interval in the line would be some starting point and an ending point. So how many intervals are there in this stuff? There is A1, A2, A3, A4, A5, A6. Okay, there are 6 intervals. Now I construct a graph using these 6 intervals, wherein every interval represents a vertex. Every interval represents a vertex. So how many vertices will be there in my graph? 6 vertices. A1, A2, A3, A4, A5, A6. Now there exists an edge between any vertex I and j if the corresponding intervals overlap, right. So there exists an edge between vertices ai comma aj if and only if intervals corresponding to ai comma aj overlap. Okay. Now A1 A2 there is an edge, A1 A3 also there is an edge, then after that no other edge from A1, A2 A3 there is an edge, A2 A4 there is an edge, A2 A5 also there is an edge. Okay. A3 to A2 only there is an edge, nothing. A4 A5 there is an edge, and A5 A6 there is an edge. Let me define a variable, a term called click. What is a click of a graph? It is a subgraph that is completely connected. It is a subgraph that is completely connected. I want to have the maximum click here. The maximum click of this graph is 3, right. A1, A2, A3 is connected. Take, right. You can't find 4 vertices such that every one is adjacent to every other, correct. And I can't, so the maximum size click is 3. Okay. So I leave it as a very simple exercise. What you need to do is you will sort all the intervals in terms of this end point, starting point and ending point, in terms of the starting point, and then just do a traversal from left to right. So what will happen? A1 is added. Okay. Now what is the max click I have seen so far? 1, right. Then A2's start point, so this is called left point and right point for every interval. A1's left point has come, so A1 is added. A2's left point has come, it is added. So max click is 2. Now A3's left point has come, then it is added, so max click is 3. Then what happens? A1's right point has come, so A1 you remove. So max click still remains 3, I have only 2 fellows here. Now after that A3's last point has come, so A3 is also removed. Now the number of element is 1, but max click remains 3. Now A4's first point has come, so A2, A4, there are 2 but still, okay, and now A5 has come, right, A2, A4, A5, again max click becomes 3, A5 has come. Now A4 gets removed, then A2 gets removed, then A6 comes, so A6, A5 is there, then A5 gets removed and A6 gets removed. So when I scan from left to right and keep adding something into the basket when I see a left point and remove them from the basket when I see a right point, I can go and find out what is the size of the maximum click, right. So if there are n intervals, to sort them in some order takes n log n time. After that, to find the maximum click, it takes just order 2n time or order n time, okay. So the point is, given an interval graph, I can go and find the size of the maximum click in order n time, order n log n time, where n is the number of intervals. You able to get this? Yes or no? Yes, no, yes. So there are 2, 3 clicks here, A2, A1 and A3, and A2, A4 and A5, that also we forgot, okay. I thought A2, A4 and A5 is also a triangle, in sense they are adjacent. Okay. Now why are we learning this in the context of register spilling? Okay. Now what will happen is, suppose you are going to design an architecture. Now you are expected to go and run some programs on that. So this architecture need not be a general purpose computer, it can be a high performance computing, it can be a computer for doing database, it can be at database transactions, it can be a computer which is trying to do a web based transaction, it can be a computer which is doing some digital signal processing, it can be a mobile phone, it can be a baseband computer, it can be a computer that needs to sit in a router. So we could have several types of processors today, network processor, embedded processor, programmable logic controller class processor, microcontroller class processor, desktop class processor, server class processor, what more, we can keep on listing more. For every type of processing today, we have some workload. Workload is the type of programs that we will execute. A collection of such type of programs, it basically is called a benchmark suite. Suppose I want to design a server class machine today, it's, let us say web server, then there are benchmark suites which will be representative programs that will run on your architecture. These are available. These are available at a huge cost. This is a big business. Selling benchmark today is a business. So there are many benchmark suites that are available. Let me just name some of them. You go to Google and find out more about them. Spec is a benchmark. EEMBC is a benchmark. There are database benchmarks. There are web-based benchmarks. There are benchmark for network processing. What is it's called benchmark suite. Why we call it a suite? It will be a collection of programs which are representative programs that will be running on a system. We have mobile benchmarks today. Now when I am designing an architecture for say some field X to solve some problem X, for example I want to do something for microcontrollers that sit in your washing machine, your things, etc. Right? Simple microcontrollers that even control your nuclear reactor. All small and big things. Now there are some embedded benchmark. EEMBC actually gives you a set of embedded benchmarks. So you take these benchmark programs, right, and do what we call as a liveliness analysis. What do you mean by a liveliness analysis? Now let us go back to compilers. I want to teach some very interesting fact about compilers. Compilers are in two parts. So when the compiler, a single compiler comprises two parts, one is what you call as architecture independent part. Another is architecture dependent part. Architecture independent part and architecture dependent part. In the architecture dependent part, you do all your code optimization, first code generation and code optimization. That is, you translate the code into the machine language of your target architecture. Suppose it is x86, I translate into x86 assembly programs, right. While the architecture independent part takes your C code or whatever high level code and make it into what we call as a 3 address code. This is basically an intermediate representation. A 3 address code is nothing but one opcode like add, and etc., and 3 operands, operand D, operand S1, operand S2. This is how a 3 address code looks like, where operand D is the destination operand, S1 and S2 are source operands. So your entire program is translated into an intermediate representation, which is a 3 address code, in which I would have 3 or 3 or less than 3 operands, and the maximum size is I will have a destination operand, 2 source operands. Okay. So this is basically a 3 address code. Now this 3 address code is basically translated to what? To the corresponding machine code. Now this type of constructing a compiler is extremely useful for designing the next generation architecture, because the first part, when I compile, I can compile it on any machine, and that is independent of your architecture. Now I am trying to design an architecture, so I need a compiler which will give me something which is independent of this architecture. So this 2-stage construction of the compiler, what sometimes they call it as, this is the front end and this is the back end. This 2-stage construction of the compiler is extremely useful for me to design my architecture, correct. So the front end and the back end. So what I do, I want to design a new architecture, I take all, so suppose I want to do it for say web transactions, I just take all the benchmarks, representative benchmark for web transaction, I compile it using any compiler and I stop it at the first, at the front end. So I will have the 3 address intermediate representation of all my programs. Okay. Now the 3 address implementation would be something like add R1, R2, R3, subtract R4, R1, R2, add R6, R1, R2, R4, and again add R1, R5, R6. Okay. Now this is an intermediate representation. So I will just say, I will keep it as O, right, sorry. I do not want to confuse it as registers. So I will say O1, can you just say R1, R2, R3, right, O1, O2, O3, what was sub? O4, O1, O2, add next one 06, 01, 04 and 01, 05, 06. Okay. These are operands. Now, when I do O2, O3, see in an instruction, whatever is there on the left hand side is the updated, is the variable which I am updating, okay, right, and what essentially I also call it as I am defining the value of that variable. Whatever is on the right hand side, I am only using that value, right. For example, in this add O1, O2, O3, I used O2 and O3. This is nothing but O1 equal to O2 plus O3. This is the right hand side and this is the left hand side. I used the variables on the left hand side. I used, please note here, I used the variable on the left hand side to define or update the variable on the right hand side. Okay. So, O1 is valid, it comes to life whenever it is defined, and that life or that avatar of O1, okay, is valid till when? Till it again gets updated. You are getting my point? So, a variable or a operand actually comes to life when it is updated or defined. That is, it is in the first entry of this 3 address code, or when I model it as an equation like O1 equal to O2 plus O3, it is on the left hand side of that equation, and its lifetime is there till it does not die, or its new avatar starts only after when it is defined next. And in this avatar it need not be useful always, till it is used it is it is alive. After you stop using, you can go and redefine it later, but if you stop using at some point, then it is almost dead, okay. So let us take this. So there are 4 instructions, let us call it as T1, T2, T3, T4, because the program is going to execute in this order. Let us say add is going to get executed in T1, then this will be T2 is T1 plus 1, T3 is T1 plus 2, etc. So every one unit of time it is going to. So let us draw the timeline here. So for O1, it will start with T1 and end with T3, because T4 again it is going to get defined. Now the next avatar of O1 will start here and it can go wherever it wants, right. Similarly, O2 right, just to make that thing little bit interesting, let us make this O2. O1 started at T1 and it is valid till T3, okay. After that O1 is not used, assume the O1 is not going to be used. Similarly, O2 started somewhere, okay, and it stopped at T2, okay. Now, and again it is going to start at T4 and probably it will go for some. So O3 started somewhere and it stopped, let us say O3 was here till T1, O3 was here, and let me say that this is also 3, okay, it is going to be used till T4. Because O3 is used till T4. So it started somewhere and it is going on. And O4 maybe there, it was not there for add, O4 again starts at T2, and let me say this is O4, T2, and it goes on O4, and O6 actually starts at T3. Right? Now, at any point of time, if I can maintain all the live variables in registers, I am done. Okay? If I can maintain all the live variables in registers, that is enough for me, right? My program is going to execute fast. So, for example, at T1, what are all the live variables? O1, O2, O3, all the three are live variables. If all the O1, O2 and O3 are available in register, then please note that T1, the add operation will go very fast. When I go to T2, please note that O1, O2, O3 and O4, right, are live variables. If I have all of them in registers, I can do that thing very fast. No, sorry, yeah, O3 is still there, right. Now in T3 again, now I see O1, O3, O4, O6 and so on. So if I have 4 registers, I can do the whole thing very fast, right. There are 5 variables there, O1, O2, O3, O5, O4 and O6, but if I have 4 registers, I can do it very fast. Suppose I had only 3 registers, what would have happened? Since the load store architecture, O1, O2, O3 will be on registers. Then I want next, when I want O4, O1 and O2, O3 should have been sent to, when I come to this particular instruction, O3 should have been sent to where? Memory. I should have moved O3 to memory, and then I can use O1, O2 and O4, correct. So this is example of a register spilling. Are you able to follow this? Because when I move off O3 to memory, at this point again I need O3, at T4 I need O3 here. So I have to bring it back from memory. Are you able to follow? Right? So if I don't have 4 registers here, then there is a certainty that there will be a register spill. If I have 4 registers, this particular snapshot can be done with all the variables maintained in registers, and which is necessary, right. In a load store architecture, it is a must that all the variables of non load store operations are in registers, right. So how do I calculate? So what is this representing? This is again a set of intervals. I can take the, I can construct a graph here from this interval, right, and the size of a click is equal to the, at any point of time, the size of overlapping, the number of overlapping intervals represent the size of the click. The size of the maximum click tells me the maximum number of variables that are going to be live at any point in this program, right. The size of the maximum click of this interval graph, size of the maximum click of this interval graph basically tells me the maximum number of variables that are going to be live at any point in this program, does it not, right. So now given this interval diagram, now I can construct an interval graph as we did in the previous part, and on this, sorry, okay, I can construct an interval graph, and from that I can find the maximum click, and that maximum click will tell me for this benchmark program, this is the maximum number of variables that will be alive at any point of time, and so if I have that many number of registers, I can execute that program without any register spilling, correct. So what do? I take the entire set of benchmark programs, and in these benchmark programs I do the liveliness analysis. This is called a liveliness analysis. How long a particular variable is alive, that is what we are doing, right, in this here. How long a particular, so I do this liveliness analysis, construct interval graphs, find the maximum click of these interval graphs, and at maximum of those maximum clicks, size of the maximum would be the number of general purpose registers I would like to have. Now if that is too high, then we will strike a balance with a caution that yes, for some classes of benchmark programs, even within benchmark you could have varieties of benchmark program, some classes of benchmark programs, this will have memory spilling and it will take some more time. Okay, you able to follow? So this is how we go and decide on the maximum number of registers while making an architecture. Are you getting this? So let us very quickly, I am looking at load store architectures. Load store architectures, I need to have every operation done on registers. I cannot afford to have memory spilling. Compilers have two phases, a front end phase and a back end phase. I am designing the architecture so there cannot be a back end for my compiler. So this type of a compiler constructions helps us. Now we go and look at the front end of that compiler, we get what we call as a 3 address code. From the 3 address code we go and do a liveliness analysis. We construct an interval graph, find the maximum click of this interval graph, and that will tell me for all the benchmarks, and that will tell me the maximum number of GPRs I need to have. Okay, this is okay. So this is one very nice example where graph theory is used, concepts in graph theory are used for constructing architecture. I just want to cover this in this course because you get a link to the other courses that you are studying. So when you go and sit in some math course or graph theory course, don't think it is waste of time for computer scientists. It's very, very useful for computer scientists. Okay, right? Any doubts? Yes, you had a doubt.
So what are the valid operations in the analysis, like add, subart? You have mentioned add and sub.
Anything it may be. See, as long as, see, with a variable I can do, as long as I am getting defined, whether it's true add, div, sub or some operation which you and me define, some fuse, multiply, add, something like that. As long as my value changes, that variable becomes alive till it is being used. Somewhere you stop using it, then you say goodbye. So in the compiler course, the first part of your compiler course, probably 1 month or even lesser than 1, you will learn what is a 3 address code. The 3 address code will have some generic set of operations and the structure as I have shown you in this place, right? This type of a structure, right? And from that you do and you can decide, okay? Because this doesn't need an architecture. Okay. You can use C compiler for, so the front end is independent of architecture. So I just use a C compiler and just say do the front end part alone. So I don't need to use a C compiler for x86 architecture or anything. This is architecture independent. I stop at the middle. I cut the compiler into 2 halves. So let us take even an x86 compiler or an ARM compiler, no problem. I will remove the bottom portion, then both the compilers are same. So normally how do you construct C compilers? You have one compiler with a machine independent part, architecture independent part, then you have an architecture dependent part. So the front end of all GCCs will be the same, the back end only will change. So I take just the front end and generate this 3 address code and do this analysis. Right. So where do you compile this program? You can run the compiler on any x86 or any Timbuktu machine, as long as I get the 3 address code. After that I do the analysis on that same Timbuktu machine. But finally from that I will find out how many GPRs are necessary for my machine, correct? Is it okay?